broadband amplifier. Now before starting that, let me tell you something. Why I am not supplying you the PDF of class notes. That the class that we are taking, I am not supplying you the PDF of the class notes. The reason is very simple. In the first class, I gave you the places where you will get the books, textbooks or reference books, on the materials, some of the papers, everything I gave there. Then beyond that also, every class I am mentioning in the initial slide this website. Look at this website, https://ocw.mit.edu. OCW is Open Courseware. ocw.mit.edu //high-speed-high-speed-high-spring-high-spring-high-spring-pages/lecture notes. Go to this site. There you will get the PDF version of each lecture that we are discussing. So there are about 25 or 28 PDFs available there corresponding to each lecture. You can download those lectures and you can read those lectures. Therefore, I am not supplying separately PDF version of the lecture notes. That is one reason. Other reason is, if I supply you the lecture note, it is basically a wastage of time and resources. I have to upload that in my email. That will take time, and you have to download it from my email. You have to come to my email and download it. That will again take time. If you download it from this site, it will be much faster because that has a larger bandwidth. This site has a larger bandwidth. So downloading from this site is much easier than downloading it from my emails. So based on that, I am not supplying the PDF lecture notes. So you can do that. You can always get the PDF lecture notes. It is at your fingertips. Now let us revise what we discussed in the last class. We discussed about the characteristics of a broadband amplifier. We said that what is amplifier? It boosts the signal levels to an acceptable level. Amplifier is the fast circuit in any receiver or in any transmitter. This one is the fast circuit. So typically the input signal is amplified or boosted up. Then it provides reverse isolation. The key performance parameters for amplifier are its gain. Gain we discussed in some length. Again we see that bandwidth, noise and linearity. These are the four parameters of the amplifier. We also discussed a common source amplifier as an example, considering the MOS FET, and we saw what is the DC gain, what is the 3 dB bandwidth, and what is the gain bandwidth product. So expressions for this we also saw. Then we discussed about Then we discussed about the gain bandwidth trade-off, which means we said that gain bandwidth product is a constant. If we increase the gain, then the bandwidth will decrease. If we decrease the gain, then the bandwidth will increase. So that we discussed about this plot also in the last class. So, and how to improve the gain bandwidth product, that also we discussed. How to improve GM by C total. GM by C total is proportional to VGS minus VT by L. So these things we discussed in the last class. Then we made some observations. I think here this is the point where we stopped in the last class. So from that point, let us come to the today's class. Here what we will do is, for the time being, we will assume that for bandwidth analysis, the amplifier that we are using is loaded by another identical amplifier. So you can see in the picture there are two amplifiers. On the left side is an amplifier which is the first amplifier. Then the output of the amplifier goes to the second amplifier. So there is a second amplifier. Now in the output of the amplifier, you will observe, you will get the output signal as well as besides the signal will be there. Then in terms of circuit, in the output you will see some amount of capacitance. So C output. Then similarly for the amplifier, in a input amplifier we will have C in. So C total is C out plus C in plus C fixed, whatever fixed amount of capacitance we have giving, that is fixed C fixed capacitance, so that there will be matching. So if we have matching between these two amplifiers, then as you know, from maximum power transfer theorem, we should for maximum power transfer there should be matching between the input and output. So input and output should be complex conjugate of each other. That is what we are doing here. C fixed is ensuring that C out and C in, they are matched. That matching it is ensuring that way. Now what are the intrinsic performance of an amplifier? The intrinsic performance is, it is defined by the bandwidth achieved for a given gain when C fixed is negligible. If you do not have any C fixed, or it is almost zero, then the amplifier approaches the intrinsic performance as its device sizes are increased. Device size will increase means it can carry more current. This you can know by assuming this impedance, looking at impedance or resistance. The more the resistance, then you know what will be the current. The current will be more if you increase the size of the resistance. The more the resistance, the less is the current. The less the resistance, the more is the current. The size of the resistance, a resistor, if it increases, then its resistance decreases. Size decreases, resistance increases. So that is why amplifier will approach its intrinsic performance, that is the best performance, as its device sizes are increased and the current, they are increased. Both are increased. In practice, a point of diminishing return for bandwidth versus size and power. Size means once you go to size determines what is the power. The more power, the larger size you require. Otherwise, if it is a smaller size but you give more power, it will burn out. Small size cannot handle more power, it will burn out. So the larger the size, the larger is the power. So a point of diminishing return for bandwidth versus size or power of the amplifier is roughly when C in plus C out is equal to C fixed. If these two are equal to C fixed, then when you take C in plus C out minus C fixed, that is equal to 0. So that gives you the main return point. Now let us consider a single amplifier and the Miller effect. This Miller effect basically is concerned with impedances which connect the input to the output of an amplifier. So here you can see we are taking an amplifier. Its input is Vin, input impedance is Zin at the input point, the input impedance is Zin. Then input to output impedance there is one ZF, and then output impedance is Zout, output voltage is Vin, and in the output we are connecting an impedance ZL, which is the load impedance. Now if you consider this circuit, for this circuit you can find out what is Zin. Zin is equal to Vin divided by Vin minus Vout by ZF. This comes from your close to knowledge. If you know the voltage difference, you can find out what is the voltage difference, then the voltage difference, voltage by voltage difference divided by ZF. This comes from the Ohm's law, circuit theory, Ohm's law, Kirchhoff's law, that you know. From that you can find out what is Zin. Zin is equal to Vin by Vin minus Vout. Vin minus Vout is the voltage difference between output voltage and input voltage, and that divided by ZF. That is what is Zin. So that will be equal to ZF by 1 minus AV. AV is the voltage gain. So how do you get it? That is AV. So the first point Vin by Vin minus Vout by ZF. Now ZF is in the denominator of the denominator, therefore ZF goes to the numerator. So that will be Vin into ZF by Vin minus Vout. Then you divide the numerator and denominator by Vin. So it will be ZF by 1 minus Vout by Vin. Vout by Vin is the gain. So you can write that 1 minus AV. AV is equal to Vin minus Vout by Vin. So Zin is equal to ZF by 1 minus AV. Similarly, we can find out what is the output impedance. For the output impedance, it is same as the input impedance, only you will change Vin and Vout. Vin will become Vout, Vout will become Vin in the same expression. So this becomes Zout is equal to Vout by Vout minus Vin divided by ZF. Take ZF to the numerator and divide the numerator Vout in the numerator and denominator. So that becomes 1 minus Vin by Vout in the denominator. Vin by Vout is equal to 1 by Vout by Vin. 1 by Vout by Vin is 1 by AV. So Zout is equal to ZF by 1 minus 1 by AV. Since AV is large, usually the gain of the amplifier is large, therefore, or the amplification of the amplifier is large, therefore 1 by AV is small. For AV large, 1 by AV will be small compared to 1 that can be neglected. So Zout is approximately equal to ZF when AV is much greater than 1. Now let us consider the example for Miller capacitance, Miller effect. Now let us consider Miller capacitance. So between input and output, instead of we were using ZF, so for ZF, this impedance will be capacitive impedance. So consider CGD in the MOS device as CF for the Miller capacitance. Assume gain is negative, so we will have a negative gain. So amplitude of the gain is positive, but gain is negative. Gain is negative. What does that imply? it implies that the output and input are out of phase, 180 degree out of phase, that is indicated by negative gain. So it does not say that gain is low. Negative gain does not say that gain is low. Gain is high, or the amplitude of the gain or magnitude of gain is more than 1, but their phase are 180 degree out of phase. Okay, and now otherwise instead of ZF we are using CF here. So if we are using CF, then its impedance is ZF will be equal to 1 by SCF. S is J omega. So Zin, input capacitance Zin is equal to 1 by SCF by 1 plus AV amplitude, which is equal to 1 by SCF into 1 plus AV amplitude. So this looks like much larger capacitance by AV. If you look at this, the capacitance is much larger once you consider AV, because AV is large. So capacitance is J omega is fixed. J omega is fixed. So now CF effectively becomes CF into 1 plus AV. So Z is equal to 1 by J omega C. Now here J omega remains as it is. C is equal to CF into 1 plus AV. As you increase AV, C will increase. So therefore, it looks like a much larger capacitance when we are considering the Miller effect. The Miller capacitance is much larger when you consider the gain of the amplifier or the amplification factor. Now, let us look at the output capacitance. Output capacitance will be 1 upon SCF. So this makes sense because the input of the amplifier is virtually ground, so gain has to be larger. So when gain is large, basically the input is virtually grounded. So that is what it says, 1 by SCF. So that indicates that the input is virtual ground. Okay. Next. Now let us see an example of amplifier, Cmos inverter amplifier. The Miller effect, it gives a quick way to estimate the bandwidth of an amplifier without solving the equations. Using only intuition, you can estimate the bandwidth of an amplifier. Let us look at some example. Assume that the bias, V bias for the amplifier is nominal. Output is such that Nmus and Pmos transistors are all in saturation. We are considering an inverter here. So Nmus, which is the device, and the Pmos, both the devices are in saturation. You can look at the circuit. The circuit has two MOS transistors. One is the Nmus, the upper one is the Nmus, lower one is the Pmos, or N-type MOS, P-type MOS, that you can see. So these are the two amplifiers that we are using. So in those are working in saturation. If both are in saturation, then this topology will be very sensitive to V bias. Because if biasing is changed, then you will go away from saturation. Therefore, it is very sensitive to V bias. Biasing determines whether you are operating in active region, saturation, or in cutoff. Therefore, they are sensitive to V bias. So some feedback biasing will be required in this case. Now, here you can see what is the total C. C total is equal to CdB1 plus CdB2 plus CGS1 plus CGS4. Now, dB1, dB2 are for the amplifier 1 and amplifier 2. GS3, GS4 are for the amplifier 3 and amplifier 4. So then plus K is the Miller multiplication factor into COV3 plus COV4 plus the C fixed. So C fixed is there. Then we have the Miller multiplication factor for the for the capacitance. Then we have the capacitances due to each device. So that gives you C in and C out that we discussed earlier. C in and C out, that comes from these two. CDB1 plus CDB2, that is giving you C in for the second one. Similarly for the second one, CGS3, CGS4, that gives you the capacitances for the output. Now GS, you know, G is for gate and D is for drain. Now based on that, the transfer function for the CMOS inverter will be like this. If you look at this figure, the transfer function will be something like this. C total, you know, we have given seen in the C total. Now the transfer function, when you consider the transfer function, that gives you, if you give some input, what is the output. So basically the transfer function gives us a plot between the amplified version of the input signal or the amplification factor, which is V out by V in, its variation with frequency. The maximum value in the saturation, it will go to GM1 plus GM2 into R01 parallel R02. Also that will be the maximum value that we have seen in the last class. That will gradually decrease after we reach the frequency 1 upon 2 pi C total into R01 parallel R02. Up to that point it will be constant. After that it will start decreasing and it will reach a value of 1. Amplification of V in will be equal to V out when we reach this point GM1 plus GM2 by 2 pi C total. So at that point, when F is equal to GM1 plus GM2 by 2 pi C total, at that point V out is equal to V in. So that is the total bandwidth. So starting from 0 up to that much. This bandwidth is a low bandwidth. This is not a high bandwidth. This is a low bandwidth depending on, because it depends on GM1 plus GM2 divided by C total. If you have a larger C total, the bandwidth is low. So see, for large C total, we have a lower bandwidth. So this effectively we get in this structure a lower bandwidth. The bandwidth is low. Now, what we will do is we will add a resistive feedback. If we add a resistive feedback, then you will see that the bandwidth, instead of going staying at GM plus 1, the GM1 plus GM2 into R01 parallel R02, that was the gain. That gain decreases to GM1 plus GM2 into RF. So that instead of having a high gain, it decreases a little bit, but it is not going to 1. So it is still more than V in. So it comes down, but the range where it is parallel to the F axis, that range, real bandwidth, that is increasing. So that you can see, instead of being 1 upon 2 pi C total into R01 parallel R02, that has now changed to 1 by 2 pi C total RF. So using RF, a resistive feedback resistor, this gain has the bandwidth has increased. But you can also see that we have increased the bandwidth, but gain has decreased. So gain bandwidth product remains same. That we have not changed. Gain of bandwidth product remaining same. we could increase the bandwidth here. Now what is the effect on C total? In this case, what is the effect on C total? See, in the C total, you can see we are adding another term which is CRF by 2. So that much is added to the C total part. So that is the effect. And this circuit analysis, I will tell you that you try to do this circuit analysis yourself. For the fast transistor, you will write because the input is at a drain. So instead of the transistor, fast transistor, you use a capacitor. Instead of second transistor, you use a capacitor. Then you have a resistor. These three are in parallel. So those parallel things are connected to Vout, where you again put this C fixed. Then for M3 and M4, for the input part, that is gate, for the gate parts of these two transistors, you put two capacitors. So it is a circuit which is of capacitor and a resistor. When you make resistor 0, find out what is Vout by V. When you make a resistor non-zero, find out what is Vout by V. You will see these the expressions that we have done here for written. Those expressions you will find out when you do that. So that is this is simple Kirchhoff's law analysis. Therefore, I am not going into details of this. You can do this Kirchhoff's law analysis yourself. Only thing is, remember that we have extended the bandwidth. It is no more sensitive to the bias offset. So up to this point, what we have done is we have reduced the sensitivity and we have increased the bandwidth. These two things we have achieved. Now, can we do better than that? So basically, we are looking for high GM to capacitance ratio to get the highest bandwidth. That we already know that if the gain to capacitance ratio is higher, then we'll get the highest bandwidth. So that we have to maximize GM to capacitance. So GM by C, that we have to maximize. So to maximize that, what we require is what we require to know is the PMOS that degrades this ratio. So if we are using the P-type MOS, there this ratio is degraded. If it is degraded, then we cannot increase the bandwidth. Then gate bias voltage is again a constant. So these two are the hurdles, or these 2 points are the important points that we have to look into. One is PMOS will degrade the ratio when we have PMOS with NMOS. So that will degrade the ratio. Somehow we have to take care of that. And gate bias voltage is also a constant. However, when C fixed is dominant, so if C fixed is not equal to C in plus C out, approximately C in plus C out, when C fixed is dominant and power consumption is important, the PMOS increases GM without additional power. That is another important point to note. Generally, Cmos decreases the Gm to capacitance ratio, that is 1. But if C fixed is dominant, when we have a dominating C fixed, in that case Cmos increases Gm without requiring any additional input power. So you don't require any additional power, simply it will increase Gm. If Gm is increased, Gm to capacitance ratio will increase. So that we can achieve by using the dominant C fixed. Other hand, below the saturation velocity, higher Gm, that can be achieved by biasing the gate of M1 close to VDD instead of using the Cmos. So that is the other point. Below the saturation velocity, higher Gm can be achieved by biasing the gate of M1 close to VDD instead of using the Cmos. So don't use Cmos, bias M1, the gate biasing for M1 should be close to VDD. So if you do that, then also we increase this. Now, and let us start with this. Take the Cmos out of the signal path. So we do not have the Cmos. So if we do not have the Cmos, then look at this the equivalent circuit. In the equivalent circuit, if you take out the Cmos for the transistor, then you use this current source. So I bias is used as equivalent current for the Cmos. If you use an equivalent current I bias for the current source, then the circuit is equivalent to using a Cmos, BB bias too. So instead of Cmos, use a biasing current which is giving you the same current that you derive from the Cmos. So then this circuit, the left hand circuit, is equivalent to the circuit that we are using with Cmos. So we can remove the Cmos, use a current instead of that current. So when you remove the Cmos, then the gate is no longer loading the signal. Gate of the Cmos, because Cmos is not there, its gate will not load the signal, but you will get the required current that you require from the Cmos using a current source. Then Nmus device that can be biased at a higher voltage, higher Gm, up to the velocity of saturation limit that you can get. So both the things that we discussed that we will get here, this is the advantage if we take out the Cmos out of the signal path. Only issue is Cmos is not an efficient current provider. And drain capacitance close to its value Gs, signal path is loaded by capacitance of RF and drain capacitance of Cmos. These are the issues when you remove the when you have the Cmos. So these issues are also taken care of. Okay. And then use a short series amplifier instead of the amplifier that we are using. Now let us use a short series amplifier. So the circuit is shown on the left hand side, its equivalent is shown on the right hand side. On the left hand side you can see we have used a shunt resistor RS is there. Then in the output you have RL. Then with M1 we have in series a resistor R1. Now its equivalent will be on the right hand side that you can see we have excluded the current instead of, because current usually is DC, so you can exclude that for AC analysis. So the rest of the thing remains same. So use resistors. Now what we have done here is we are using resistors Rs and R1 to control the bias, to control the gain and input-output impedances. Everything is controlled by Rs and R1. This will improve the accuracy over the process, and with temperature variation, if you choose proper resistance values, then temperature variation can also not be of that much effect. Now, what are the issues that was involved in this? Degeneration of M1, usually the degeneration of M1, that lowers the slew rate for large signal applications such as limiting amplifiers, etc. So if M1 degenerates, now what is degeneration of M1? That means over a period of time, the M1 will be deteriorating. Anything that, if you know, everything in this world or in the universe has a half-life period. So after some time, its functionality will be degraded from its peak. So degeneration of M1 means that the functionality of M1 has degraded. If it degrades, then that lowers its slew rate. If it lowers its slew rate for large signal applications, that is one issue. Other issue is there are better high-speed approaches. The advantage of this one is simply accuracy. The one that we are considering is accuracy. Otherwise, high-speed approaches, there are better high-speed approaches. Now, let us look at the analysis of the short series amplification. This you can get from chapter 9 or chapter 8 of the Tomley's book. Look at the Tomley book. There in the chapter 9 or chapter 8 you have this analysis. AV or the amplification is equal to voltage amplification is equal to V out by V. Now V out by V in, you know, it is RL by RE into RF minus RE by RF plus RL. What is RE? RE is equal to 1 by GM plus R1. RL is load impedance. RF we know because of Miller effect, and RE is equal to 1 by GM plus R1. Now AV is approximately equal to RL by R1. If you consider this, then AV is approximately equal to minus RL by R1 when RF is much greater than RL. When RF is much greater than RL, then in the denominator you will have RF. RL can be neglected. Then RF is much greater than RE. So in the numerator, RE can be neglected. So RF by RF. So that becomes 1. Then R1 is much greater than 1 by GM. If R1 is much greater than 1 by GM, then RE is approximately equal to R1. So put that AV is equal to RL by R1. So that is the gain that we get. The input resistance Rin is equal to RF by 1 minus AV. This we have seen. Now you put for AV, the expression for AV here. So that gives you RE into RF plus RL by RE plus RL, which is approximately equal to RF by 1 plus RL by R1. When RF is much greater than RL and R1 is much greater than 1 by GM. Similarly, you can find out the output resistance, that is RF by 1 plus RS by R1. Now, if you use RS is equal to RL, these two are equal. Rin is equal to Rout. Both these will be same, but RS is equal to RL. So that is an advantage. Whatever is the input, that is the same is the output. Then advantage is when you use the next stage, next amplifier, then they are matched. The output of this amplifier is equal to the input of the second amplifier. So they are matched. That is an advantage. RS is equal to RL. Just if you ensure that RS is equal to RL, then we can always get them matched. The amplifiers will be matched. Maximum power transfer will occur. In this now consider the Nmus load amplifier. So instead of PMOS, remove the PMOS. Instead of PMOS, we are using an Nmus as the load amplifier. Instead of PMOS, we are using the Nmus. Now using the Nmus as load amplifier, the gain plot will be like this. The plot that we see on the right hand side, V out by V in will be approximately equal to Gm by G2. So that will be there, and the bandwidth will be Gm2 by 2 pi C total. Now if you have larger C total, then you will have smaller bandwidth. If you have smaller C total, you will have larger bandwidth. C total is determined by CDB1, CSB2 plus CGS2, CGS3 plus KCOB3 plus C fixed. Now in this, since we have replaced the PMOS by CMOS, so the capacitance is due to the replaced CMOS at CSB2 and CGS2. Now gain set by the relative sizing of M1 and M2. For M1 gain is ID1 is equal to 1 by 2 mu n COX W1 by L1 V in minus VT whole square. Similarly, M2 is ID2, for M2 it is ID2, the current is ID2, that is 1 by 2 mu n COX W2 by L2 VDD minus V out minus VT square. Now here if you compare these two, everything is same. W1 should be equal to W2 if you are using the same batch of the Nmus, same Nmus you are using. So W1, W2, or L1, L2, these will be same. W1 is equal to W2, L1 is equal to L2, those will be same. Then V in minus VT, V in is same as VDD minus V out. So under that condition, ID1 is equal to ID2. So these two, so ID1 is ID2 the transistor 1, ID2 is ID2 the transistor 2. So ID1 is equal to ID2. If that happens, then V out is equal to minus a V in plus VDD plus a minus 1 VT, where V in is equal to V in plus V bias, whatever biasing you are giving. From that you will get some value, and A is equal to root over of W1 by L1 divided by W2 by L2. This derivation you can look for any book on MOS. So the derivation you will get from the books on MOS. Now comes the design part. In the design, size transistors for gain and speed, that is the important thing. What is your speed, what speed you require, and what is the gain that you require. Based on that, choose the size of the transistor. Once you have chosen the size of the transistor, then you choose the transistor. What is the value of transistor, or what is the number of transistors that you choose. Minimum L for maximum speed. As you can see, A is equal to root over of W1 by L1 divided by W2 by L2. So L has to be minimum. If L will be minimum, then speed will be maximum. That also, you know, the larger the L, the more the signal travels within the transistor. The smaller the L, the less the signal travels within the transistor. So L is channel length. So the smaller the channel, the less the signal travels. The less the signal travels within the transistor, the less the time taken. So for time taken, to minimize the time taken, you have to have a smaller L. So choose minimum L for maximum speed. Choose the ratio of W1 to W2 to achieve the appropriate gain. Because A is equal to W1 by L1 divided by W2 by L2. Once L is fixed, then W1 and W2, their ratio will give you the gain. So gain depends on W1 by W2. Once L is fixed, L determines the speed. Now, advantages and disadvantages of Nmus loaded amplifier. Gain is well controlled despite the process variation in design of the amplifier. So that does not affect, the process does not affect. Process variation means when you design the IC design process, so photolithography or whatever, 3D printing, whatever you are using, that does not affect the gain. So gain is well controlled. Nmus is not a low parasitic load, so GS of M2 loads the output. Then this is one disadvantage. First one is advantage. Then there is biasing problem. VT of M2 lowers the gate bias voltage of the next stage. So overall lowering is achieved for M2. This severely hampers the performance of amplifier when the amplifier is designed in cascaded form. So if you have more than one amplifier followed by another, that is what is called cascaded amplifier. So there it severely hampers the performance. This issue is addressed by some researchers. You don't require to know it. Here is a paper which you can look into to know the issue, how they have addressed the issue, but it is not important from your examination point of view. Now come to the resistor loaded amplifier or on-fly silicited poly resistor. So that we are going to load for the amplifier. Instead of the Cmos or Nmos, simply you use the resistor. If we use the resistor again, you will get, instead of G1 by GM1 by GM2, it becomes GM1 into RF. And the gain becomes GM1 into RF, that much. And this is the fastest non-enhanced amplifier topology if we use the resistor loaded amplifier. On sized poly is a low parasitic load, so there will be no parasitic effects, will be minimum. Output can go near VDD, so that allows for the following stages to achieve high FT, but at the cost of gain, because our maximum gain is proportional to V RF. Then linear settling behavior is also, you can see that settling behavior is linear in the circuit. So this is in contrast to Nmos load. So with this we'll come to the end of the first part. We'll take a lunch break. After that we'll come back and start the rest of the class. So let us take a lunch break. Come at around 2:45 instead of 2:30. I'll take 15 minutes more. Since we started late, we'll shorten the lunch break. Instead of 1 hour, make it 45 minutes. So 2:45 we'll start.